Welcome to lesson 4 of this section. Now that we've discussed the theory behind a perceptron, let us begin its implementation. The first step to doing so is initializing our linear model. For that, we first need to create our model class. As usual, we define the class that we'll be using to create our neural model instances, and we'll just call it model. We will once again inherit from nn.module. And to do that, we need to import it first. So back here, what we'll do is import. Let's do it right on top of from sklearn. We will import torch.nn as nn, and our class will then be immediately followed by an init method, which can be written as def init. And as before, we use this initializer, we use this constructor to initialize new instances of this class. The first argument for our initializer will be self, where self will represent the instance of the class, the object that's yet to be initialized. After self, we add additional arguments. Our choice for these arguments is once again dictated on the basis that we are using this class to initialize a new linear model instance. Looking back at the perceptron that I showed you earlier, you can see that our model requires that we have an input size and an output size. In this case, it takes in two inputs, x1 and x2, and from these two inputs, we return one output, a prediction. But once again, we will be more general inside of our constructor. That is, the arguments passed in will be input size and output size. Perfect. And once again, do not forget to call super.init as we are dealing with class inheritance. Super.init. And having performed the necessary steps to inherit from our parent class, we will declare self.linear, which represents the instance of the class, the object that's yet to be initialized. We will set that equal to nn.linear, accepting both the input size and output size that's being passed in. All right, and now to make a prediction, we define the forward function, def forward. As before, we place self for the first argument, and arguments thereafter being the ones you need to actually pass in. How do we make predictions? Well, based on the inputs that are passed in, remember we take their linear combination and apply the sigmoid. So what we need to do is initially pass in the inputs, which we can simply denote as x. Then we set the prediction, pred, is equal to the prediction that comes out of x, being passed into our linear model. And recall that it's not enough to just pass it through our linear model. We apply the sigmoid function to convert the value into a probability. For simplicity, we can call torch.sigmoid self.linear x. All right, and we will return our prediction, and now we can use this method for any instance of our class. All right, so we finally finished our initializer. We can now use it to initialize a new linear model. And I seem to get an error, and that is because I first need to run all of my cells. So what I'm going to do is run them and fast forward this video until it does. I'll see you in a bit. All right, guys, back to our code. And now that we finished the initializer, we can use it to initialize a new linear model, which I will set equal to my model class constructor. And we can pass in two arguments into the initializer as I specified. As we specified, recall we must pass in an input size of 2 and an output size of 1 in accordance to the perceptron model we talked about earlier. And there is our linear model. Let's print out the random weight and bias values that were assigned to it. We do this by printing model.parameters. And we will print it as a list to better see the results from this output. All right, running it. Here are our parameters, and before I forget, what we want to do is ensure that random results are consistent. So we can seed our random number generator with torch.manual seed, and we can put a seed of 2. If you want consistent results as myself, feel free to use the same seed. Otherwise, you need use any seed that you want. But in essence, we just want to ensure that whatever parameters we get back, they are always consistent. So we get 2 values for the weights. This is weight 1, this is weight 2, and we get a bias. Perfect. These are obviously not the optimal parameters for our model. We've still yet to train our model. However, before doing so, as we've done previously, I like to have a before and after by plotting the data points alongside our initial linear model. So first, we must extract the model parameters. So inside this cell, we will first obtain the model parameters by unpacking model.parameters into a list of 2 elements. W and B is equal to model.parameters, and printing both values, print W and B. First, we see that W contains W1 and W2. Rather than a 2-dimensional tensor, we can view it as a tuple containing 2 elements. And we can do it like so. W.view2. And we unpack this tuple into the variables W1 and W2. And the bias term for our linear model is only a single dimension within the 0th index. So we set B1 is equal to B at index 0. All right, printing all of these values, printing W1, W2, and B1, we obtain all of them as tensor types. We can add dot item to all terms, dot item, and dot item. And what that will do is give us a Python number from all tensor values, as clearly shown. And as before, we will make this into a function called getParams, I should say, which will return the following values. It will return B0.item and the rest. All right, removing that, and we are good to go. All right, so on this cell, we plot the linear model with the following parameters alongside our data points. So we call def plot fit. The argument that we'll accept is once again a title, where our plt.title will equal the title that's passed in. And now since matplotlib is most compatible with NumPy, make sure you have first imported. Oh, I already have done that. We're good to go. We already imported NumPy. All right, and we saw that in the last video, the equation of a line can be rewritten as 0 is equal to w1x1 plus w2x2 plus 1 times b. For concision, we can just get rid of the 1. It does not make a difference. And as you might recall, x2 is simply the y value, which we must isolate in order to plot our graph. And doing this algebraically, you would simply end up with x2 is equal to, let's just comment that out, is equal to w1x1 plus b divided by negative w2. If you work the math out yourself, you should get the following values. And to make this code compatible, let's actually add the asterisk for multiplication. And that is the equation of our line. We have w1, w2, and b as they were initialized once we created our model. Now we must determine a numerical expression for x1. We already have a numerical expression for x2. So first what we do is we set w1, w2, and b1, all of that equal to the return value of getParams. And make sure to reference this as b1 as well. Our x-axis will have it go from -2 to 2. So we can simply write x1 is equal to numpy.array -2.0 and 2.0. Make sure this is an array to ensure compatibility with pyplot. And so from these two x1 points, we compute two x2 points, returning two x2 points, two y points, one at -2, another one at 2, which will be connected by a line, hence plotting our linear model. And we will plot it with plt.plot x1, x2, and given that our data set is blue and green, let's plot it as a red line by specifying the string r, and that is it. Now we also want to plot our scattered data points from earlier, and so since we will be using this code, let's make it into a function instead of copying and pasting it. Def scatterplot, fixing the tab here. We're going to press Alt-Enter to create a new cell right under it, replot our scatterplot over here, and over here as well. Scatterplot. And now on a new cell, we call plot fit, with the title being initial model. Plotting our model alongside the data points, we can clearly see that this is not the line that best classifies our data. We will need to use gradient descent to update its parameters in the direction of the least error until it learns the optimal weight and bias parameters. We will do that in the next lesson.